Welcome to Breadboarding. This is the third in the series of the Breadboard video controller, and in this video we're going to be adding the character generator and the shift register to be able to display the fonts that we load into the character generator RAM on the screen. So in the introduction video we covered a basic plan to steps to go through building a more sophisticated video controller as we go. This is step 2, so we're adding our 4KB RAM character generator and the shift register, and then in the next video we'll then be adding the 4K video RAM, so we can then actually define different characters for each cell on the screen. For the moment this character generator is just going to be driven by the address signals on the CRTC chip, so it will cycle through the characters, but it will just go from 0 to 255 and repeat that over the screen, but it should be sufficient to see what's going on. So let's have a look at our diagram. So this was what we had last time. So we have our 25.175 MHz dot clock divided down by 8 to give the character clock signal. The cathode ray tube controller chip, the 6845 compatible chip, does most of the timings and things for horizontal sync, vertical sync, and the display enable. We're buffering and inverting these signals to go out to the VGA connector. And then up till now what we've got is a fairly simple resistor based digital analog converter, and that's hooked up to a buffer chip. And for the moment, when we were testing this, we were just wiring up the various red, green, blue and intensity signals to +5 or 0 volts. And then in the update video, we did hook up some of these to the output lines of the CRTC just to get slightly different color patterns. So what we're going to do now is, first of all, we're going to add the dual port character RAM. So we'll add it into the main system bus to start with. And this is mapped at C000 to CFFF and is using the address decoder Y2 signal. Then for now what we're going to be doing is the row addresses are going to be hooked up to RA0 to RA3, which are the standard row address counters coming out of the CRTC, and those are going to be the bottom A0 to A3 lines, and we'll see why that is in a minute when we look at the fonts. And for the moment we're just going to be feeding 8 data lines into the other address range. Now, under normal circumstances, this is where the current character cell on the display would be fed into the character RAM. But for the moment, since we don't have the video RAM at the moment, what we're going to do is just feed in the signal from the CRTC. So this will mean that the characters should repeat every 255, 256 characters and just repeat down the screen, but that should enable us to check to see if the characters are looking okay. So then in order to output the character bitmap to the display, what we have to then do is to feed each line of the character, which is made up of 8 bits wide, into a shift register, and we load that based on a character latch, and the character latch signal is in fact one of the signals we were using in the previous video. It's actually the one that's used to do the clear. So this is one with a kind of 1/8 duty cycle, and then that shift register is clocked by the dot clock. So once we load in the bit values for the current row of the character, then the dot clock will rotate that around, and then the output value of that is either going to be a 0 or 1. So should this pixel be displayed or should it have the background color? And what we're going to add here is just a multiplexer chip. So what this does is, based on this signal here, it chooses either one input or the other. And the way how we're going to do this for the moment is we'll just hardwire the foreground or background colours so that it'll determine whether it's foreground or background. In later videos, the input to the colour multiplexer will come from memory as well. So we'll be able to define not only what character you want to be displayed in a particular cell, but also there'll be a separate byte for the foreground and background colour. And that will basically give us a 2-colour display capable of displaying 30 lines by 80 characters. So just need to remember that the character RAM is in C000 to CFFF, and we're going to need that when we come to package up the font in a format that we can load down onto the NanoComp. So now we need to look at what fonts to use. As a really good site here with a collection of fonts, and these are fonts which have come from graphics cards and various PCs over the years. It's also got other early computer forms, so Amigas and various other non-IBM computers, and all the various fonts and character sets from there. We're just going to be choosing two, so I've got a VGA one which is 8 bits wide by 16 bits high. We've also got a CGA compatible font which is 8 bits wide and 8 bits high, and that came from the earlier generation of cards. And you can download the fonts and you can download this basic DOS utility, but there aren't many good utilities for looking at fonts, and this one, Fontraption, is not a bad one. You do need to run it on the DOSBot, but you can see here you're able to select individual character cell and see what the bitmap is for it, and it knows about loading 8 high characters and 16 high characters, so it's not a bad little utility. I do have it running, so it's probably a little bit difficult to see, but what I've got here loaded is the VGA character set. You can see within a particular character we can go through, we can change individual cells and things, so you can edit the characters if you want to, make your own, and then you can go through the display. So 0, look at that one, yeah, that's 219 I think is that one, and obviously most of these default to the A character. Now we've found some suitable fonts for using on our display, so we'll be using the VGA 8 bits wide by 16 high. What we now need to do is to work out how to download these onto the Nanocomp. So if you remember, the character RAM is at C000 to CFFF in the memory map, and we will eventually burn this into the ROM, and eventually we'll modify the monitor to copy it into RAM at reset, as well as initializing the CRTC. So what we need to do is convert the binary font file into SREC and to load at C000. So there is a utility called srecord which is available at these URLs. I'll include these in the description of the video. And there's a Windows version of this as well. And this command line, there's a fair bit to it, but what it basically says is convert the binary VGA 8 F16, set it at an offset of C000, disable the data count record, so there's an S5 record that includes a data count. We don't want to include an S0 record, and we want the execution start address to be 0 and a footer. So what that basically does is makes all the addresses start at C000, prevents the S0 record, prevents the S5 record, and then outputs an S9 record at the end. So if we have a look at the command line for this, so I've already got the command line in there for the VGA one. That's worked as well. So let's just have a look at those files. So if we look at the VGA SREC one first and open with Notepad++, you can see here Notepad++ is using the language option here for srecord, so it's highlighting the checksum and the address. You can see starts at C000 and goes all the way down to CFFF, and then we have our S9 record on the end there as well. And each of these lines here, if we look here, is 64 characters there, so that makes it 32 bytes. So starting at E, and this will be F, and this is FF. So these files should now load into memory. When we use the Nanocomp load feature, we should just be able to load these font files straight into the character ROM memory when we have it all up and running. So we're just going to look at the components that we're going to be using. I've already put the chip labels on here. So this is the dual port RAM. I think it's 48 pins, so 24 down each side. And you can see that we've got a load of pins for input output for the data left and right. And we've also got the address lines at A0 to A11, both left and right. So the advantage of this is that the processor can access the RAM and the video controller can access the RAM at the same time, and you won't run into any complications caused by the two clashing. On some early computers, you used to could get snow on the screen, so interference on the screen, when both the computer and the video controller were accessing the character memory at the same time, so this avoids that particular problem. In some of the later videos when we add single port RAM, which is, we've got some larger, faster single port RAM, which the disadvantage of not having dual port is outweighed by the size of the RAM chip. So these are only 4K, unfortunately. The ones we're going to be replacing it with in later videos are 32K and slightly faster as well, about 15 nanosecond access time. So I've also got here these are ALS versions of the chip, so these are the higher speed ones, so they can go up to 40 megahertz. And the 74ALS 166 is a serial register, so there is a load signal that loads the A to G bits in, and then the clock signal then rotates those out through the output port. The QH port is effectively the output, so that output there is our 10, choose which color you want coming out of there. And then the 74ALS 157, that's a multiplexer. So we basically have 4 outputs, and for each of the outputs we have an A and a B input. So we've got 2 inputs, 1 output, and dependent on the selection value here, then we'll either choose A or B. And obviously what we're going to use for the selection is the output from here. So if it's a 1 or a 0, we're going to choose the foreground or the background colour. As far as other components, just a few decoupling capacitors and lots of 3 and 4 hole red and black ground and 5 volt wires just to hook everything in. Let's just have a quick look at our schematic diagram. So in the update to video 2, we showed where we rewired some of the connections around here, so I won't go back over that. And what we've got down here is this RAM here is going to be the character RAM, and this RAM here is going to be video RAM. Well, we're not putting this video RAM in now, but we needed to really do this to make sure we were getting the layout right. And the reason why I'm putting the character RAM over here is this one's not going to change, whereas this one we're going to swap out in a couple of videos time for the larger, faster RAM. The reason why we need larger, faster RAM is these aren't big enough to be able to do any sort of graphics. So we need to use larger RAM chips for that. But to simplify this, to make it easier to do this, I was just going to use these 2 chips. In the first version of the video I produced, I was able to actually squeeze everything into one chip because I only went up to 25 lines by 80 characters, and because that was 2000 bytes, I was able to actually put the color and the character 1 byte beside each other. But that resulted in lots of complicated latches and lots of timing and delays and pipelines and things like that. So in order to keep this simple to start with, I thought I would stick with these 2 chips here. So we're going to be installing this one, and we're going to be installing this one, and then up here this is our multiplexer, which is taking our input from down here. So if we look here, we are taking the row values out of this character ROM here, or character RAM here. We're feeding it into the chip here, and then the dot output here, if we just select that, the QH dot output is going all the way up here, and this is actually the foreground background selector going into the selector input here. And you can see that the B value selects foreground, the A value selects the background. So in fact the background is 0, the foreground is 1. So that's the way how our fonts work. The white or foreground color is 1, background is 0. And then this is just wired into the red, green, blue and bright signals that we had previously. And all we're going to do for the A and B inputs here for the moment is we'll just tie those to ground or to 5 volts. So to start with, we could just use black for the background and white for the foreground. So we'll just put perhaps all the A's to 5 volts and all the B's to ground. So then the character RAM chip, the right hand side, we're going to hook up to the main computer bus. So we've got the data bus here that's just going off to the rest of the data bus. Now I've already wired up an area on the video card for the data bus, so we don't have to wire this in all the way up to the other side of the board, just needs to go up to the video card. And then the address lines here we're going to wire into the address bus on the main bus strip on the card. Then we're going to need to wire in the row address pins from the CRTC up here down to the address 0, 1, 2 and 3 pins. And then for the moment, since we're not going to have any of these other address signals, so the A4 all the way up to A11, we're not having this chip. So I think what I'll probably do is just wire these in to the memory address lines up here, a bit like we did with the previous video and the colors. We'll just hook this up to 8 of the address lines so that we get the values going from 0 up to 255, and we should be able to see those characters appearing on the display. Then the output of each of those characters is going into our shift register, and the shift register is loaded on the character latch here. Now that character latch is coming from the clear signal that we got out of here, and if you remember in the previous videos, this provides a low pulse for one of the clock cycles out of 8. So if you look at 8 bits being sent out by the dot clock, then this one goes low on the 8th bit. So that character latch causes the next row of pixels to be loaded into the parallel input to the shift register, and then after it goes high and the dot clock starts shifting that around, then the values will come out of here and will go into the dot output here, and then that will just be turning our red, green, blue bright signals on and off, and we then should see our characters. So that's what we're going to be doing there. Okay, so let's now look at how to lay out the board here. So we need to put the RAM down the bottom here, and because it's so long, we need to really be careful about where this overlaps with the values here. So I think we've just got about one pin free there, and then it goes on to the data bus that we've got going up there. That's okay. We probably need to leave more gap on this side, just because we're going to have the address lines coming in here, but then we need to fit a cable in here to go from over here over into the other side there, because the address and data lines on this side are also going to be connected up to here. The only difference will be the chip enable signal will be going to a different value, but other than that, they all need to be wired up the same. So I'll probably get some of the ribbon cables to go over here, so it'd be better to have a bit more space here. It might make it a bit tight up here for our data wires and things, but I think we should be okay. So we just need to make sure the chip is okay. So it's plugged in. What I'll do is I'll put in a few of the things in first, and then what I'll do is I'll wire all of this up, speed it up with a dubbed over commentary, so we don't have to wait for every single wire to be plugged in. But let's just put the power in first. It's always a good idea to put the power lines in first in case you forget, because it's not generally good for the chips to be running without power. They may get, so again, normally I try and make sure these chips have a parallel sort of link up to there, but because we're tight on space here, then we'll just do that there. So then we need to allow the space for the other chip to go there. So we're not going to put that in at the moment. It can probably go a little bit, it might be able to go a little bit further up, or we need to route these wires around here. And then we've got the shift register. We can probably give this a little bit more space up here, because we are going to have the data wires coming around here and coming around here. So we'll just move this to here, and we've got sufficient. We can always move these in a later version if it's not a big problem. So that's our 74ALS166. Clip that in. We need the multiplexer to be able to have the outputs to go to the buffer for the video input, so more of a gap. So just finished wiring on the wiring up the multiplexer there. Now we're going to be wiring in the Y2 chip enable signal here, looking at the control signals at the top here. So read, write, chip enable signals, the Y2 chip enable coming in here. Tick those off. Then we're going to be wiring up all of the address lines here. So this is A0 up to A11. So this allows the CPU to be able to access the character generator RAM. And after that, we're going to be hooking up the data bus. So we have a copy of the data bus signals just above the chip here on the breadboard. So we'll just be wiring up D0 to D0 to D7 to D7. It just so happens the order of the signals is the other way around, so D0 is at the top and D7 is at the top on this one, so we just have to be careful wiring that up. We're going to put in the control signals for the other side, wiring the row address lines to A1, A0 to A3. Then we're hooking in the memory address lines just to provide some temporary character values. So these will rotate the values from 0 to 255 when we're doing this. Check those off. Now I need to install the shift register, so set a number of the lines, and we'll also need to include the clock counter and the latch signals. The output here is the bit output for controlling the foreground and background colors. Then we're just going to hook in the data lines here. So this is the raster output from the character generator. We are then feeding into the shift register. Once we've done that, we just need to do the multiplexer. So we're hooking in the red, green, blue and intensity into the video DAC, and then there's just a few other of the control signals we need to put in, and we're wiring all of the background to ground and the foreground to 5 volts. Right, so now we're ready to test this. There was one minor change I did. I was checking against the first version of this project I did, and I noticed that the OER and the CER signals I had reversed. So originally the Y2 signal was going into the output enable and the chip enable was set to ground, and all I've done is I've swapped them around just to make them the same as the previous project. So that's the only change I've done. And what we need to do now is to download the CRTC register program. So I've got the CRT1 SREC from the last video. So we're just copying the full path name to that. I've got a session of real term here, so we're just going to paste in the CRT1 SREC. I'm going to switch on the nanocomp, and I'm now just going to load this. So do send file, and there's an F on the display to say it's finished, and I'm just now going to press go 000. Now if we just switch to the document camera, you'll be able to see what the current image. So I'll just turn the light off here so it's a bit clearer. So you can sort of see it's a random pattern, not really very much at the moment. What I'm going to do now is to send the SREC record for the character RAM. So I've just copied the VGA16. And what you should see is when this is loading, so I'm just going to put the nanocomp monitor into load mode. And what we should see is when I send this file, you should see the characters start to populate this as the bits get downloaded. So let's just see if this works. Go. And we can see as the memory is being populated, then the character raster is being populated and our random characters are disappearing. Excellent. So that's proved that it's working. We can see at the top here that the first character is a blank and the last character in the line, you can't quite see it here, but it's half of an O. If we look at the character set here, you can see that the 0 value, 00 is there. And in fact, given these are rows of 16, we've got 1, 2, 3, 4, 5 rows of 16. So O is in fact the 80th or 79, 0 to 79, 80th character. So we would expect to see a blank character at the beginning and the O at the end. And in fact, when we look on the display, we can in fact see there's a little bit of bleeding of a character left over from, there's about half a character at the beginning here. And we can see here that there's only about half of the O here. And this is what I was talking about in some of the early videos, that the display enable signal in particular needs to be offset by, you know, 1 character cell or half a character cell, something like that. So in one of the future videos when we're going through and actually tuning some of these signals so that we get a really good display. But it's pretty good. I have counted there are 30 lines, so we can actually see the bottom line here is 30, and we've got our 80 columns across here. So that proves that the thing's working. I'm just going to do one little change. If we wanted to change the background color, then what I can do is just change one of the links on the multiplexer. So the multiplexer's currently got all background at ground and all foreground at 5 volts. I'm just going to change the 3A signal, I think it is, to 5 volts. And you can see now that by doing that, we now get a blue background. If I just turn the light off here, you'll probably get a better view of that. So this means our character ROM is working. And if we wanted to just show that we can modify the characters, what I'm just going to go here first of all is go to the first character location, which is memory C000. And if I change this to FFF, what we should see is this first character at the top just before the smiley face. As I do FFF, we should see row by row that fill in to be solid. So I'm just going to do that now. So first FFF, next FFF. That's about, we've done about half of it now. So you can now see that half of that cell, character cell, has been filled in, and we'll just carry on doing the rest of them. So the advantage of having the character RAM is that we can do some level of high resolution graphics just by using some custom characters. So you can see now I've now put FF in the first 16 bytes of the character RAM. So we've shown that that is in fact working. So that's great. That's all I wanted to do in this particular video. What I'm going to do in the next video is to add the video RAM. So that means that we'll be able to define what characters we want to appear at what position. We're still only going to have a foreground and background color to start with. We're building this up step by step. So hopefully if you found this interesting, please hit subscribe so you don't miss future videos. And if you can also hit like as well if you found it interesting, it just helps to push the videos up the rankings so more people can see them. Thanks for watching.